So today we'll start our next class. So today we'll start tutorial 2. Tutorial 2 is this tutorial is mostly focused on second law of thermodynamics. So this means that the concept of entropy will be very important. Okay, so now with that in our hand, we will start from our first problem. So problem 1. So our first problem, so let me write the first problem. Identify x and y in del h del p at constant s equal to del g del x at constant y. So the options are this: a x equal to t and y equal to b. Option B is x equal to v and y equal to p. Option C is x equal to v, y equal to t, and option D is x equal to p and y also equal to t. So these are the four options given. So you have to basically figure out what is the value of x and y. It's t or v or v or p or v or t or p or t. Okay, so and before doing that, let me just explain a brief. So here h is basically h is basically the free energy, or it's called enthalpy, and G is basically the Gibbs free energy. So this is the definition of H and G. So how to do that? So in order to do that, first what we will do, we first calculate, first have to write the expression of H. So H is basically U plus PV. Here U is basically the internal energy, P is pressure, and V is volume. So now dH equal to du plus pdv plus vdp. So now we all know from first law of thermodynamics that first law of thermodynamics, dq equal to du plus dw, right? So du we can write it like this: dq minus dw. So du will be, dq means t ds minus pdv. So now this thing will be substitute here, which will basically gives us dH equal to tds minus pdv plus pdv plus vdp. So now you can write it dH equal to tds, pdv will be cancelled, tds plus vdp. So So this is basically the differential form of this enthalpy. So this is basically the differential form. Now from this expression we can write it like this. Okay, so T we can write it like this, right? TH as del H by del S at constant pressure, and V we can write it like this, right? Del H by del P at constant S. So yeah, del H del S into constant, so del H del P. So this is okay, right? So temperature can be written like this, as del H by del S at constant pressure, and V volume can be written like this, that is del H by del P at constant S. Now similar way we can write the Gibbs, for Gibbs free energy also you can write the Gibbs free energy as H minus Ts. Now H you already know, H is equal to U plus PV minus Ts, right? So now G, so the total expression of G will be this, U plus PV minus Ts. Now we can write this like similar way, just like how we did in like for enthalpy case. We write it in differential form. So similar for Gibbs free energy also you can write it in differential form. So for that we have to write it like this, dg equal to du plus pdv plus vdp minus tds minus sdt. So now here also you can substitute this first law of thermodynamics in this expression of dg. So now that will basically gives us du as tds minus pdv plus pdv plus vdp minus tds minus sdt. So now here what will happen? So basically pdv will cancel out each other, and we will have this expression in our hand, and also TDS also will cancel, right? So so now the whole expression is VDP minus SDT, right? Now what we can do now, the similar way DG, this is the differential form, right? This is the differential form. So this is the differential form of the Gibbs free energy. Here this was the enthalpy. So now for here also we can write the volume as V as del G del P at constant temperature, and entropy as minus del G del T at constant pressure, right? So this is, so we can write volume as del G del P at constant T and entropy as minus del G del T at constant P. So now from these two results and these two results, what you can see, the common quantity that we have calculated from both this differential form is the volume, right? Here is the volume that is expressed as the partial derivative of enthalpy as constant S, and here from Gibbs free energy also you have calculated the volume, which is the partial derivative of Gibbs free energy with respect to pressure at constant T. So we can equate that, right? So that means that del H del P at constant S will be equal to del G del P at constant T, right? So now, one second. So now if we see our question here, so in the question what it is asked, del H del P at constant S will be equal to del G del X at constant Y. Now so you have to basically found what will be the X and Y for this problem, right? Now from our results also you can see del H del P at constant equal to del G del P at constant T. So So if we compare it with the question, we will get P will be equal to here x, right? P will be equal to x, and sorry, so it will be other way around. X will be equal to P and y will be equal to T. So this is our final answer, right? So now if we check our answer, so here you can see, so one second, so the correct answer will be x will be equal to P and y will be equal to T. This will be the correct answer, right? So this is the problem. So let me just briefly explain it once again. So here basically in the problem, to calculate del H del P at constant S equal to del G del X at constant Y. So what will be the value of, what will be the expression of X and Y? So in order to do that, first we have taken the expression of this enthalpy H, and that will be equal to U plus PV, and we then calculate the differential form. So that is basically dH equal to TdS plus VdP. From there we have calculated T equal to del H del S at constant P, and V will be equal to del H del P at constant S. Similar way, we have to calculate the same thing for Gibbs free energy also. So here also we have calculated Gibbs free energy. So dg, so this is the expression of Gibbs free energy. So if you write it in differential form, so this will be basically dg will be pdp minus sdt. This is the differential form, and if you compare it, you will get volume as del G del P at constant P, and entropy will be minus del G del T at constant pressure. And if you check the question, so from that we can write del H del P at constant S will be equal to del G del P at constant T, and if you equate with the question, you will get x equal to P and y equal to T. Okay, so this is it. Now let me go to the next question, question number 2. Okay, so question number 2. So basically here it states that 1 mole of oxygen expands diabatically against a constant external pressure of 118, right, until the pressure balances. Now the initial temperature and volume are 200 degrees centigrade and 20 liters. So these are the initial temperature and volume respectively. Now I have to find out the change in entropy. That is, the units will be in joule by Kelvin inverse. Okay, so the options are, let me write, 1 minus 1.906, B is 1.172, D is 1.906, C, this is for C, D is minus 1.172. So this is the problem. So basically so what happens that 1 mole of oxygen gas expand adiabatically against a constant external pressure. So that means adiabatically, that means dq is 0 for the whole process against a constant pressure until the pressure balances. So the initial temperature and volume 200 degree and 20. So what happens basically here, so both pressure and volume are changing during this process, but the temperature remain fixed here, and so, and the external pressure is external pressure is mentioned here, that is 1 atm. So basically what we have to do now, we know that for adiabatic process, so let me write the first law of thermodynamics for adiabatic process. So we have to calculate the delta S, right? What is the change in entropy? So for that we have to first write, we'll start from the first law of thermodynamics, okay? That is dq equal to du plus dw, right? And here for the case dq is equal to 0. So now we can write it like this: d equal to minus dw. So now here basically gas it's expanding by itself, so uh, the work done by the gas. So what happens here, dw will be equal to is here minus pdv, right? Because in this case gas is expanding by itself, so will be minus minus will be plus pdv. So du basically equal to pdv, and du we already know is equal to tds ptdv, right? So now we can write it like this: ds will be p by t into dv, and from ideal gas law we already know, right? pv equal to nRT. So we can write p by t equal to nr by v into dv. So this is the form. This is the last form we will get. So this is it. Now if you do the integration both side, we will be getting delta is equal to, so nr, so dv by v, so this will gives basically gives us a log. So that will be log, let's suppose this is vi to vf, right? So delta is so si to sf. So vi basically, vi and sf basically the initial entropy and the volume, and sf vf are basically the final entropy and volume. So let me write it like this then. So it will be sf minus si will be equal to nr ln vf by vi, right? So this we can write it as delta S, that is change in the entropy that we will be calculating. So nr ln vf by vy. So we will basically, why we have done this thing, because we know here both the pressure and volume is changing, so we have write the pressure in terms of volume, and we'll by doing that we'll get this formula how the entropy changes. And for this problem we'll be basically using, and this formula is only applicable for adiabatic process, okay? Because applicable for adiabatic, because for in order to in order to use this formula, the dq needs to be 0. That means the process has to be adiabatic process, okay? Now let me write the information that is given here. So so basically it's written that 1 mole of gas, right? So number of mole will be 1 mole. R is, we already know, that is 8.314 joule per mole into Kelvin. This is basically the gas constant. Vi is the initial volume, that is 20 liters. But Vf we have not the answer for Vf is not given actually, but since the temperature so Vf is not given here, so but since in the final step, like the pressure will be, we know at the final step Pf basically would be the 1 atm, right, at the final, and temperature will be 273 plus 200. We know that pressure is given at 200 degrees centigrade, so we have to write in Kelvin, right? So that would be 473 Kelvin. So this will be the TF also. So although the VF is not given here, but using this PF and TF and using the first law of thermodynamics, using the ideal gas equation, you can calculate the VF, right? So that will be PF into VF into NR into TF. So VF will be NR TF into PF. So that will be basically 1 into 8.314 by PF, and PF is basically here 1 second. So PF is basically here 1 ATM, right? So that's it. Now what we will do, uh, so this will give us the volume. Sorry. So this will basically gives us the volume. So now what we will do, so VF will be this. So so this will basically gives us NRTF. TF will be this 473, and all of these things are there. So now so that's it. Okay, fine. So now what we'll do, we'll calculate the volume. Okay, we have calculated the volume. Now we'll substitute all of this thing here in this formula. Okay. So delta S will be, N is 1, R you already know, that is 8.314 into log of, if you substitute this, that will be 8.314 into 473 by 20, right? Now let me calculate what was the value of 8.314 into 473 divided by 20. Okay. Now if you do the calculation del for delta S, you'll be basically getting give as the problem itself. The problem is you should have to calculate in Joule by Kelvin, right? So we substitute all of this. So this will basically gives us delta is equal to 1 point. Just calculate this thing. Okay. This thing, just calculate this delta S. If you calculate this, you'll be getting the delta is equal to 1.172 joule per Kelvin. Okay, so this will be the value of delta S will be getting. Okay, so now this is the delta S will be getting. So here this should be the correct answer. Okay, just take care of the units and all. Okay, just be careful what the units are using. Okay, and if you just carefully put the units in a proper way, then you will be getting this 1.172 joule per Kelvin as a result. Okay, so now this is the problem 2 is done. So here what I have done similar way. So first for adiabatic process, we have calculated the expression of delta S here, and after that as initially the PF and TF was supplied in the problem, so but we need the VF because in the problem VF is needed. So we have calculated the VF from here, and after doing all of this thing we have got delta is equal to like this. After substituting all the value VI, VF, ANR, everything, and after calculating this delta S, we'll be getting this is 1.172. Okay, so now let me go to the next problem. Problem number 3. Okay, just let me check once again everything is recording perfectly or not. That's fine. So So now the problem number 3. If you have some problem, you can ask. Now going to the next problem. So let me write the problem number 3 first. Maximum entropy of mixing is achieved when two ideal gases X and Y are mixed in the amounts of, okay, basically you have to calculate for which case. There are 4 cases are given in the options. For the which case the maximum entropy, I mean for which case, like the amount of X and Y that is mixed gives you the maximum entropy. Okay, and the options are A, 1 mole of X and 3 mole of Y. Option B is 3 mole of X and 1 mole of Y. Option C is 2, yes, because one of this moles of X and 3 moles of Y. Option D is 2 moles of X and 2 moles of Y. So these 4 options are given. So for each cases, so what you have to do, like for each cases, when this fraction of X and Y is mixed, you have to calculate for which case the entropy will be maximum. Okay, before solving this problem explicitly, let me just explain what is this entropy of mixing is. And what happens, like let's suppose this is a container and there is like a wall, rigid wall between this container. So let's suppose there is a gas X and there is a gas Y. So let's suppose V1 amount of gas, V1 let's suppose the volume, and V2 is the amount of Y gas. Okay, so now, and let's suppose this system is isolated. Okay, so isolated means it's not like able to like make any kind of contact with the surroundings. Okay, so this is basically isolated system. So what happens, let's just suppose we remove this wall. Okay, so what will be happen here? So both this X and Y will be mixed, right? So X and Y will be mixed now. So now total volume will be now Vf equal to V1 plus V2, right? So what happens here basically? So uh, although only the mixing is happened, but still because of this mixing I will show you that there is some change in the entropy of the system is happening here. So we have discussed, right, in the previous problem. So for isolated system, this will be the change of entropy here, right? So let me write this thing once again. So delta S will be NR ln Vf by Vi. So let's suppose for let's suppose for X gas. So for X gas, what is happening here? Initially, the Vi's volume is V1 and Vf's volume is V1 plus V2, right? So delta S will be nr ln v1 plus v2 plus v1, right? So that means for x there is a change in entropy. Similarly for y also, let me, for y gas also, xi is initially equal to v2, sorry, this is vi. Vi was initially v2 because initially the volume of the gas, volume of the y gas is contained into this, only into this v2 volume. So initial volume of the y gas was v2, and just, so initial volume was v2, then the final volume of y gas, for y gas, vf, was v1 plus v2, right? So now what happens here? So for y gas also, that means for y gas, delta sy also nr ln v1 plus v2 by v2, right? So for y gas also there is a change in entropy because of the y gas is mixing with x gas. Okay, so the net change in entropy is delta sx plus delta sy. So the main thing, like the main point I am to try to explain here, that when two gas is mixing, okay, so because the volume of the each gas is also expanding, each individual gas is expanding, so for that kind of case the entropy of the total system will be also increase. Okay, so this is the main thing that I am to want to explain here. So this is basically called the entropy of mixing. Okay, this phenomenon is known as entropy. So I basically gives you a mathematical uh, formulation, like how this entropy of mixing is give a rise to the change in the entropy of the whole system. So that's it. Now we'll focus on our problem. Okay, so in the problem, so now in the problem, one important thing is here it is to note that here the thing is that here the volume is not mentioned. Instead of mentioning the volume, they have mentioned the mole. The mole of the gas is mixed up. Okay, so also we'll just have to this change in entropy formula we'll also have to modify as the as for our problem the moles of the gas is given. So let me write, this is called the delta S. So this is the delta S mix. Okay, mix I am writing is as a suffix because it basically signifies the change in entropy due to mixing. Okay, so now I'll write this thing for mole, fraction of mole. So delta S mix will be minus inner summation over xi into ln of xi. So xi basically is the fraction of the mole. Okay, so here xi basically is the ni by n. So n is basically the total number of moles. Okay, and this is basically the fraction of ith gas. Okay, fraction of in terms of mole. Okay, you can write it as fraction of ith gas. Let's suppose there are I is the summation index. So let's suppose there is n number of gas in the system. So that means summation index I will be varying from 1 to n. If there is n number of gas that are mixed for this system, but in our system there is only two gases. So for our case n will be equal to 2. Okay, so now let's consider the A. So for A, what has been 1 mole of X gas is mixed with 3 mole of Y gas. Okay, so basically for A, X will be sorry, I will write it as ah, x will be, this is small x, this is in capital X, okay, right? This small x is like the fraction and this capital X will be the uh, gas, x gas. Okay, so x will be 1 by first case will be 1 mole of x gas with 3 mole of y gas. Okay, so x gas with 1 by 4, so basically that is 1 by 1 plus 3, that is 1 by 1 by 4, and x of y will be 1 3 by 1 plus 3, that is 3 by 4, right? Now for this case, delta S mix will be minus nr 1 by 4 ln of 1 by 4 plus 3 by 4 ln of 3 by 4. That's it, right? Now nr 1 by 4 you all know is 0.25, ln will be 0.75, 3 by 4 is 0.75 plus ln of 0.75. Now if you calculate this thing, you will be getting minus 0.560 as delta S mix. This is for case A. Similarly, for case B, this will be small x will be for second B, case B, 3 moles of x is mixed with 1 mole of y. So x will be 3 by 3 plus 1, so 3 by 4, and x of y will be 1 3 plus 1, that would be 1 by 4, and it's also gives you the same, right? So delta S mix will be same, right? It would be again like in previous options, the fractions are basically got interchanged, okay, but the result will be getting same, right? In this case also same, 0.563 will be getting, right? Now we will consider the option C. Option C, 2 mole of X gas and 3 moles of Y gas. So for option C, X will be 2 by 2 plus 3, that means 2 by 5, and X of Y will be 3 plus 2 plus 3, that means 3 by 5. Okay, so now we'll be substituted here. So delta S mix will be minus nr, so 2 by 5 ln of 2 by 5 plus 3 by 5 ln of 3 by 5. So now if you substitute the, if you calculate the log of this and all these things, you will be getting, and after substituting in and r value, you will be getting this as minus 0. Just calculate this thing by yourself also, right, to recheck if everything is here or not. Okay, but I have also calculated previously, so this will basically give you delta S mix is minus 0.672. Now for the last case, that is D. For D, what information is given? So for D it is mentioned that 2 moles of X is mixed with 2 moles of Y. Okay. So now X will be 2 by 2 plus 2, that means 2 by 4, and X of Y 2 by 2 plus 2, that means it is also 2 by 4, that means basically 1 by 2, 0.5. so delta S mix will be minus nr into 0.5 into ln 0.5 plus 0.5 into ln 0.5. okay, now if you calculate this will be basically giving you if you calculate this, I have already previously calculated, so from that I can I can write it like 0.693. So now if now we have to compare the values, so this is pretty straightforward, right? So now here first we have get it for A and B, we get minus 0. Don't focus on the minus sign, because we have calculated the maximum change. Okay, it doesn't matter whether it's negatively change or positively change, you have to calculate the maximum change. Okay, so the mod value only you have to consider here. Okay, so for option A and B we got delta S mix as minus 0.563. For option C we got minus 0.672, and for option D we got minus 0.693. So so the answer will be very interesting here. So the so answer will be, so for D case the delta S mix will be maximum, right? So the correct answer will be option D. So just let me explain what I've done briefly once again. So first I have discussed about the entropy of mixing, like how, like if you have two or more than two number of different gases, and if you mix those gases, and as the volume expands, so basically there will be change in entropy, which is called as entropy of mixing. And because of and for now, for our problem, we have to calculate this entropy of mixing for like different fraction of gas uh, that is mentioned in the problem. So for different cases, so this is basically the formula that we are using. Xi is basically the fraction of the gas. So for first option A, that is 1 mole of X gas is mixed with 3 moles of Y gas, we have calculated it. Similarly for option B, for opposite situation, 3 moles of gas is mixed with 1 mole of Y. 2 mole of, say option C is 2 mole of X is mixed with 3 moles of Y, and option D is 2 moles of X is mixed with 2 moles of Y. And for each case we have calculated the delta S mix, and we have find out that when like this equal amount of gas, like 2 moles of X gas is mixing with 2 moles of Y gas, we get a maximum entropy. Okay, right? Even if you option C, if you see the number of gas, like the total amount of gas is higher for option C, but we still get the correct answer as option D, because here the equal number of X gas is mixed with the equal number of Y gas. This is basically one of the like important like phenomena that we are seeing here. Like when equal amount of X gas is mixing with equal amount of Y, we get the maximum change in entropy. Okay, so this is the option, this is the problem, problem number 3. Okay, now we'll be going to the problem 4. Now let me write the problem 4. Basically this is a true false kind of a problem that we have also deal with in previous tutorial. Okay, so problem number 4, in an irreversible process, enthalpy of the universe decrease. Uh, so so basically this statement we have to like support whether it's true or false. Okay, so before solving the problem, let me just tells you which is the like one of the main like fundamental law in or law in thermodynamics, that is the entropy law. Or you can say basically this is also, you can consider it as a second law, a type of a second law. So what this law basically states that in this is let me write law of entropy. Okay, so in any irreversible process, the total entropy of the universe always increases. So for irreversible process, the delta S of universe will be always greater than 0. Okay, and for our case also, it's an irreversible process. So for the case that is considered in the problem also, the delta S universe will be always greater than 0. I mean the change in the entropy in the universe. So universe basically means that delta S system plus delta S surroundings. So the addition of change in entropy of the system and change in entropy of the surrounding. So that's addition, like if you add those two, change in entropy, that basically gives you the change in entropy of the universe. So that thing will be always greater than 0 for irreversible process. Okay. So now in the problem we have asked not the entropy but enthalpy, whether there is the enthalpy will be increase or decrease. In the problem it asks that whether it will be decrease, it's true or false. Okay, whether it should be true or false. Okay, so uh, let me write the expression of enthalpy, that is H equal to U plus PV, right? But if you carefully see the expression of enthalpy, there is basically no entropy terms involved, right? I mean entropy is not this this enthalpy is not direct measure of entropy, right? So so on the basis of that you cannot fundamentally just by using just by using this thermodynamic fundamental, you cannot tell that whether enthalpy will be decrease or increase. Okay, so so we cannot say that H delta H for universe will decrease or not. It can be changed, but you cannot confirmly say that it will be decrease or increase, because delta H cannot H cannot gives you a direct measurement of enthalpy, right? So maybe enthalpy change, but you cannot confirmly say that it will decrease or increase. Okay, so basically this statement is not true, so this statement will basically false statement. Okay, so this is it. So this is problem number 4. Now I hope you understood how it's done. So this is a very the main thing is that for irreversible process you have to remember this thing always. Okay, for irreversible process delta S universe will be always greater than, this is some fundamental thermodynamic law. But as enthalpy cannot capture this direct change of entropy, so we cannot confirmly say whether it will be increase or decrease. Okay, so on the basis of that, this statement we cannot consider it as true. Okay, so that's why I've chosen the answer as false. So now problem number 5. Okay, so problem number 5. So the problem, now for the problem of the 5, so the question is the entropy of the universe for a reversible process remains constant. Okay, so these things have to say true or false, whether it should be true or false. Now this is also like in order to solve this, you also need a very important concept in the law of thermodynamics that I have not like mentioned in the previous problem. That is purposefully because I know that this statement is needed in the second problem. Okay, so basically we already know, like for irreversible process. So one second, let's check. So basically, so for irreversible process, we know delta S, delta S universe is always greater than 0. That is irreversible process. That is, the entropy will be always, for the whole universe, the entropy will be increasing, and delta S universe is basically the delta S in system plus delta S in surroundings, right? So, but for an reverse, if the process is a reversible process, for reversible process, delta S universe will be 0. That means the entropy, there is no change in entropy. If there is no change in entropy, that means that entropy should remain constant, right? I mean, the entropy before occurring this reversible process and the entropy after the process is occurred would remain same, right? So that's why the total change will be equal to 0. So from this thing we can state that in a reversible process, the system and surroundings undergo changes in such a way that they can be reversed. This is the main thing, they can be reversed without any change in entropy. This is it, right? So from this we can tell that as universe should be like it should remain constant, right? Remain constant. So the answer will be true. Okay, so that's it. This is the problem number 5 we have done. Okay, this is like two very important like concepts that we need to know. First is like for irreversible process, the the entropy of the universe should be always increasing greater than 0, but for a reversible process the entropy should remain constant. That means delta S universe should be equal to 0. Okay, so now to the next problem. Problem number 6. So for problem number 6, delta H and delta U for the, so delta U already know is the change in enthalpy and change in internal energy. So these two quantity have to calculate for the reaction at constant temperature are related as. So basically this how for a reaction, let me write a reaction first. If E2O3 is reacting with 3H2, basically gives you 2Fe plus 3H2. This is the reaction. Okay, just focus on the moles, like number of moles that is used during the reaction. So the question is for this reaction, how this delta H, that means change in enthalpy, is related with delta U, that is change in internal energy, right? So also let me write the options. So option A was delta H should be equal to delta U. Option B was delta H equal to delta U plus RT. Option C was delta H equal to delta U plus 3RT, and delta, and D is option D is delta H equal to delta U minus 3RT. Okay, these are the four options are given. So what you have to do now, so here let me first write the expression of enthalpy in differential form. Okay, so that we have already did, right? Like in a previous, if you saw a previous problem, like here, this is it, right? This is the same thing. Okay, right? Now we write this thing for this problem also. So now instead of dh, I will write it is as delta H. Okay, delta H equal to delta U plus P delta V. Okay. Now here, as you can see, there is no information of like pressure, volume is changing, right? So but you can see the number of moles of each component, like the total number of moles, like in this reaction, like before the reaction, after the reaction got changed. Okay, but that is only the information that you can get from this reaction. We cannot get any information from like how the pressure is changing, the volume is changing. Okay, the only quantity which change we can like figure out from this equation is the mole. And for this reaction, uh, so okay, so let's first write this change in enthalpy in terms of mole. Okay, so delta H should be, in that case, would be basically equal to delta U, and from ideal gas equation, you know, PV equal to nRT. Okay, so PdV will be definitely delta N into RT, because temperature, it's in the question, it's already mentioned that temperature is fixed, so delta N is the only thing that can be changed, like in the right hand side, if there is change in the left hand side. Sorry, if there is change in left hand side, so here this is as delta V. So in right hand side, only thing that can be changed is delta N, that is number of moles. So for here, delta N will be NF minus NI. NF basically is the final mole, that is 3 moles of this Fe plus 2 moles of Fe plus 3 moles of H2. So 3 plus 2 minus Ni was Fe2O3, that is 1 mole, and 3 H2. So 1 plus 3. So basically this gives you one more thing is important here. So that I actually miss in the problem is that uh, in the problem the state of this reactant uh, and a product, like it's is it in solid state or liquid state, that is also a very important thing in this system. So I forgot to mention that. So this is in solid, this is in gas, this is in also solid, this is in so we are not, for in the thermodynamics we are only dealing with gas, right? We are not dealing with solids. So we have to consider H2 as ideal gas, right? So delta N should be here, the change in mole, that only applicable for gas. So NF basically is, delta N basically will be moles of gases products. Products means this is basically the product, right? This is the product, this is the reactants, right? So for product minus moles of gases reactants. So moles of gases product is 0 because there is no gas products in this side simply. So 0 minus 3, because there's 3 moles of H2 is there, which is in gas, so which gives you minus 3. Delta N basically will be minus 3. So now if you just substitute this delta N minus 3 into our main formula, so delta H will be, this should be delta right here, plus delta N RT. So delta U plus delta N will be minus 3, right? Minus 3 RT. So this is how change in enthalpy basically related with change in the internal energy. So let me just briefly explain it once again. So this is the problem, like for this reaction basically you have to calculate what would be how does delta is change in enthalpy is related to delta E. And for that we first write this differential form of delta, how delta is related to delta U, and from there P del there is there as there is P del V in P del V in the expression, but in the problem there is no information of change in pressure and volume is mentioned. So only thing that is changed is the number of moles. So we have to we have to rewrite this P del V into as del N RT. Now del N simply is a change in mole, but change in mole only for gas only for uh, gas systems. Okay, because this all these things, thermodynamic quantities that we're calculating only applicable like for like gas system, like ideal gas system or real gas system. So here in this equation this H2 is only the component that is in gas state, right? So initially there is 3 moles of 3 moles of gas, we can say it, but in final state there is no gas is there. Okay, so mole of gas of products will be 0 because in the product there is no gas, but for reactant there is 3 moles of H2 is there, so that's why minus 3 we will write. So 0 minus 3, that gives us minus 3. And now we'll substitute this thing in this equation, that gives us delta is equal to delta U minus 3RT. Okay, so this is how this thing is related. So the correct option will be option D, right? Yeah, option D. So it is problem number 6. Now we go to the problem number 7. Let me write the problem number 7. Hmm. Problem number 7 is this: the Clapeyron's equation helps to calculate. So 4 options is given. Option A, latent heat of vaporization. And option B is boiling point or freezing point. Option D, vapor pressure at one temperature if the vapor pressure at another temperature is given. An option, this is option C, and option B is all of the above. Okay, so before solving this problem, let me just write like what is the like Clapeyron's statement in a form of equation. Okay, so basically here we have to consider the clauses, because here most in the answer in the options, if you watch carefully, the vapor system has been considered here. Okay, so we have to write the Clausius-Clapeyron's equation for the vapor system. Okay, and for the vapor system, so the Clausius-Clapeyron equation basically tell us that this CC equation is actually a formula, which used to determine the variation of vapor pressure with temperature. So basically how this pressure of vapor is changing with temperature, that thing we can calculate using this Clausius-Clapeyron's equation. Okay, now so let me write this function, this like equational form of this formula. Okay, so basically log of P2 by P1 will be equal to L by R into 1 by T2 and 1 by T1. So let me just state each and every term in this equation. So P2 and P1 are the vapor pressure at temperature T1 and T2 respectively. Okay, so P2 P1 basically is the vapor pressure. Like in a vapor, if you change the temperature, okay, definitely like the pressure should change, right? So how this change is happening, to calculate that, we basically use this Clausius-Clapeyron's equation. Okay, and here L is basically latent heat. Now this is basically the statement of the Clausius-Clapeyron's equation. Now in the problem, so in the problem there are like four options as given. The first two options basically are the latent heat of vaporization, boiling point or freezing point. These two things you can calculate, but uh, but in order to calculate that, there should be sufficient other information should be like provided for the problem. Okay, like you can calculate this basically this L, that is the latent heat, but in order to calculate you have to know this T2 T1 P2 P1, but that condition is not like mentioned in these two options. Like it's not mentioned it like this, like if like P2 P1 and T2 T1 is provided, then you can calculate the latent heat. If in the option it's written like that, then you can like easily take option A or option B as a correct option, but as it is not written that, then we have to discard these two options. Okay, but for the last option, not last option, for the option C, third option, if you see this, you can easily calculate, right? If like we know the latent heat of vapor, okay, everybody knows it. If T1 T2 and P1 we know, like temperature of in the problem, if you see, it's already given vapor pressure at one temperature. If we know like vapor pressure at one temperature, let's suppose it's T1, at T1 temperature we know the P1, then the vapor pressure at another temperature. So P1 at T1 P1 we already know. At T2 what is the P2? Okay. L you already know. So these things we can easily calculate, right? R is the real ideal gas constant. So this option C you can easily calculate, like from the problem. Okay, so for this, so mm, so now from here, if you see, so if P1 is given at T1, then we can easily calculate P2 for a T2. Okay, this thing you can easily calculate from this Clausius-Clapeyron's equation. So the correct option will be option C. Okay, right. So this is how we have to do. So this is basically a very important. So this equation you basically have to remember, like if you for a vapors, if you change the temperature, how the pressure of the vapor is changing. So in order to calculate that, this is basically the equation. Okay. So I will just box this equation up. Okay. This is problem number 7. Now we go to the problem number 8. Problem 8. So problem 8. 1 mole of an ideal gas at 2 atm expands irreversibly and adiabatically into vacuum to decrease its pressure to 1 atm. Now the change in entropy is to calculate basically. So how to do that? So how to do that? So basically to do that, what you have to do, so so let me first write down all what are the things are given and what are the things you have to calculate. Okay, so irreversibly and adiabatically. So it's adiabatic. First it's adiabatic. So adiabatic process. So delta Q would be equal to 0, right? For a diabetic process. Next thing is uh, 1 mole ideal gas pressure vacuum. So pressure finally reach 1 atm. Okay, I have to calculate. So initially it was P initial was 2 atm, right? Then it's like expand, so its pressure got decrease, and it goes to a final pressure of 1 atm. In this whole thing is happening in a vacuum. So you have to basically calculate what is the change in entropy. Okay, so external pressure is basically at 0. Okay, P external is 0. So that means basically there is no work done involved here also. Okay, so now as the volume is expand, so this is an ideal gas, right? So you can use as it's ideal gas, we can use EV equal to nRT equation, right? So this type of problem we have dealt with earlier, right? So n is also 1 mole, n is 1. So as the gas expands, of everything is like in the problem if you see. So 1 mole of hydrogen to vacuum. So so temperature also remains like fixed, right? T is also fixed in the system. T is fixed. Okay, so now delta S you already know. So this for uh, adiabatic process, the so the delta S change in delta S would be simply equal to R ln V2 by V1, right? This will be basically change in delta S. So but also we know that from Charles law, P1 by P2 will be equal to V. So P1 V1 equal to P2 V2 from Charles law, right? We know that Charles law. This is basically so V2 by V1 we can write as P1 by P2, right? So delta S basically gives us NR ln P1, that is P final, that sorry P initial by P final. Okay, so NR ln 2 by 1, so NR into ln 2, that simply gives us delta. So delta should be simply n would be here 1, right? N into R is basically 8.314 into ln 2. ln 2 you know 0.693, equal to like this. So if you calculate, this will give you delta S almost equal to 5.763 joule per Kelvin. So in the problem, I forgot to write the options, but these were basically the options. A was 5.763, B was 7.683, C was 0, and D was 0.057. Here you got the option A as a correct answer, right? So this is basically using the correct answer, option A. Okay, this is problem number 8 we have already done. So similar this kind of problem we have done earlier, right? Where we have also like for adiabatic system, if a gas expands from initial volume to final volume, what would be the change in the entropy, right? So that same formula we are using, delta S, and like from the Charles law, like we have used like pressure is mentioned here, so we can like using Charles law we can like make this problem much more easier. So instead of writing the formula in terms of volume, we can write it in terms of pressure, and after that we substitute the values and we get this, and this is the answer. Okay, okay, fine. I guess this problem is clear to you. Now I'll move to the problem number 9. Okay, let's check out this recording is. So now problem number 9. So the problem number 9 is del Cv by del T at constant equal to what? Cv basically is a specific heat at constant volume. Okay. So del Cv del T will be equal to what? So the options are option A minus T del P del T at constant B into del P at constant S, or option B is T into del square P del T square constant B. Some says del S del V at constant T and del V del T at constant S, and option D is P into del square V del P square at constant T. So this was the basically this is basically these are the four options that are supplied. So here CV is the specific heat at constant volume. Okay, specific heat of the gas, I mean. So the derivative of the specific heat at sorry, this is volume, sorry, del V at constant temperature. So partial derivative of the specific heat at constant volume with respect to volume at a constant temperature would be equal to what? So now to solve this, let's first write the form of this specific heat. So we know that du equal to, right, du equal to cv dt, right, we know that. So we can write cv as simply uh, cv as del v del t. So we can write it like so: Cp equal to dq Cp dt cv dt cv dt. So from here we can write del cv del t as del t of T into del u del v at constant temperature, right? Yeah, yeah, we can write it like this, right? So now this is it. Now you already know u internal energy is du, basically is dq plus dw, right? So du equal to tds plus pdv, sorry, I write it wrong, dq equal to du plus dw, right? So du equal to tds minus pdv, and now if you take the derivative, you can write del u del v equal to t into del s del v minus p, right? Now this thing cv, so now if you substitute this thing, so del u del v here, so now it will become del t of t into, basically this will be so basically it will be, there will be t outside, so t into uh, t of del s del v at constant temperature minus p. Okay, so now this thing del cv del t, now you can write it like this: if you do the derivative del this derivative del t on this whole expression, now you will get uh, t into del s del v, then you get another t into del square s del v square, all is this constant t, minus del p del t. Okay, this will be in constant volume. Okay, so now this is del c related constant t. Yes, so now we know that now here one thing we have to use that is called the Maxwell's relation. Okay, so what is Maxwell relation? For thermodynamic potential there is a relation like how this derivative of this each of these thermodynamic function is related with each other. So in order to calculate that thing, there is a relation called Maxwell relation, so we have to use that relation. So let me SPT. So this is the way to remember actually. So del S del V at constant temperature will be del P del T at constant volume. Similarly, another is del P del S at constant volume will be equal to minus del T del V del T del V at constant and S. Similarly, del V del S at constant temperature, del V del S at constant temperature will be del P del T at constant S. Similarly, del S del P at constant temperature will be equal to minus del V del T at constant pressure. Okay, so these are basically are the Maxwell's relations. You have to remember these relations actually. So this relation basically gives us how this derivative of thermodynamic quantity SV are related with each other, provided that some of like one term will be remain constant. Okay, so now this formula we have to use in our problem also. Del S del V. Okay, del S del T. 1 second. I think there is a mistake I've done here. So here should be T, sorry, T into del T of del S del V. Okay, so now everything is fine. Okay, now everything is fine. So that is at constant volume. Okay. Okay, so now everything is fine. So now what we will do? Now what we will do is simply write this this expression you can use. Okay, this del S del V at constant temperature, del P del T at constant volume, like here you can see. So there is a T term also here, right? T term. Okay, so now after substituting the Maxwell's relation, this particular relation we will be using. So let me just write this. Del S del V at constant T will be del P del T at constant V. After doing that substitution, what will be getting? Del CV del T at constant T will be equal to, this simply become T into del B del T plus T into del S. Del S del B we can also write as del P del T, right? So that will be del T of del P del T. This is volume, this is volume. This is once again, this is also volume minus T into del P del T at constant volume. So this term will cancel. So will be del CV del T. So del CV del T basically would be T into del square P del T square constant volume. This will be the answer you will be getting at last. Okay, so del CV del T basically, so the option will be, this option will be the correct option, T into del square P by del T square. Let me just briefly demonstrate what I have done. So basically I have write this derivative of CV in terms of internal energy like this. This thing you know already. Now uh, now du dv, del u del v at constant temperature. Okay, you can write it basically write it like this, right? Del u del v. Del u del v, you can write it like this, right? Now you can substitute this here, which will gives you this equation. Now if you do the derivative of del del t onto this, so first derivative or on t will be gives you this, second derivative will gives you this on this term, third derivative on p gives you this. These three things you get. Now you have to what now new relations that you have to use in order to solve this problem, that is called as Maxwell relation. This is basically these four Maxwell relations that I mentioned here. So these four relations basically in order to solve this kind of problem, you have to basically remember all these four relations. Okay, so if you substitute this four relation in for our problem specifically need only this relation. So as you can see, there is del S del V and del P del P, both these terms are there. So if you substitute these two things in this equation, we will basically these two terms will basically get cancelled and will end up only with this term, that is T into del square P del T square at constant volume. And this is one of the options that is given in the question. So this is how you have to solve this problem. Okay, so now this is it. This is the problem number 9. Now comes the problem number 10. Okay. So problem number 10. A undergoes system undergoes a change at constant pressure and temperature, absorbing 10 kilocalorie of heat at 400 Kelvin. If delta G of the process is minus 20 kilocalorie. The delta S system calorie into Kelvin inverse is what? Now there are four options given. Okay, 2500 minus 25 and 75. So no, so first to solve this, let's first write the things that are supplied. Okay, so uh, first delta is have to calculate, right? So delta is, so first delta G, that is the change in Gibbs energy. Okay, so that's given as minus 20 kilocalorie. That is the change in the Gibbs energy. Okay, and the change in heat delta Q, that is given as 10 kilocalorie. So 10 kilocalorie we can write everything is calorie. Okay, like this we can write minus 20, because in the answer if you see its answer is given in calorie, so it's better to write it in the calorie. So that will be 20,000 calorie and this will be 10,000 calorie, right? Now uh, so now this two is given basically, and temperature is T is given as 400 Kelvin. It's constant, like pressure T and pressure is also remain constant, so no change in temperature and pressure. Now you have to basically calculate from here what will be the delta. So now we know that the Gibbs uh, previously also we have proved this, right? That is delta G equal to basically delta H minus T delta S. So here what happens, so for our case what happens here, delta G is delta H. First let's, delta G is we already know, right? First discuss about delta H. Delta is the change in enthalpy. Change in enthalpy. Now one important thing to be noted here, that for a constant pressure this delta H basically gives us the heat absorbed at constant pressure. So okay, that is the delta Q, 10,000 calorie. These things we have already done. Very first problem I guess. Let me very this here TH equal to TDS plus VDP. So how it's coming, let me also show you here. Delta H equal to TDS minus VDP. TDS basically is delta Q, na? We already know. T is the expression of TDS. And for constant pressure, dP is equal to 0. So dH basically will be dQ. This is how you can like state this thing, right? For constant pressure, delta H will be equal to delta Q. Okay. So this is given. So now we'll rearrange the equation. So delta G will be basically delta Q minus T delta S. Delta G is minus 20,000, delta Q is 10,000, T is 400, and delta S that we have to calculate. So delta S will be 10,000 plus 20,000 by 400, which gives us 30,000 by 400. So that will be equal to G by that will be 300 by 4, that's 75. So delta S will be simply 75 calorie per Kelvin. Okay, and that's one of the answer, option D. Okay, so I guess you understood how it's coming, right? So in the problem number 10, so basically in the problem, the system is changed under like constant pressure and constant temperature. So pressure is mentioned 400 Kelvin, pressure is given constant. That is, pressure is not needed for a system, the value of pressure, but delta G gives energy already given minus 20 kilocalorie, and I have to calculate the delta S of the system. So what we have done, delta G is right, delta Q is right in calorie. Then we have used this equation, like how the change in delta G is with respect to change in delta H and T delta S. Okay. Now important thing to note here, delta H you already have discussed, right? Delta is equal to T delta S into minus V delta, but T delta S already is equal to delta Q. Okay. Now here, as pressure is constant, so delta P will be equal to 0. So delta H will be simply equal to delta Q. Delta Q is the heat that is supplied, that is absorbed by the system, and that is 10,000 calorie. So you rewrite the equation like this. Delta H, now we have change the delta H is delta Q, and delta G equal to, that means delta Q minus T delta S. Then we just substitute all of this thing and we get this delta S, that is 75 calorie per Kelvin. Okay. This is the this is how this problems you need to solve. Okay, so this problem is also finished. Now we focused on the let me check whether the recording is happening okay or not. Yeah, it's happening fine. Okay. So we have done the problem number 11. Now we consider problem 11, 10, now problem 11. So 11 problem. Okay. The value of the integral, closed part integral dq by t in a reversible cycle. Okay. Option A, q by t greater than 0. Option B, dq by t less than 0. Option C, and dq by t is equal to 0. And option D, dq by t equal to constant. So now what should we do? So now here the main thing is, so for a reverse, so two way you can solve this problem. First I'll just do it like in a normal way. Okay, so this closed path means it's a closed integral. Okay, closed integral. So this means the system return back to its initial state, right? This is the meaning of a closed integral, right? Where the system starts after the integration, basically end up with that same state. Now the thing is, right, so For this case, you already know dq by t for reversible process will be simply ds, right? And uh, ds basically, what is this? This is basically change in entropy, right? Change in entropy. Now we all know entropy is a state function, right? So it only depends the final and initial state. It doesn't depends like what does process during the change in state, like the what kind of path that is taken by this process. That path is not depend on this entropy, right? Entropy only depends on initial and final state. Okay, so the thing is like here. So here that means you have to take a closed integral in ds. So if you do a closed integral in ds, so s final minus s initial, as the final and initial state both are equal to each other, so that simply gives a zero value, right? And this we have done it like in normal way, but for reversible cycle we already know that dq by t, that is ds, for from like second law of thermodynamics, that for reversible but ds is anyway equal to zero. But if you don't, if like taken into account that you don't know the second law of thermodynamics also, uh, you can simply just from this closed path integral you can just prove, right, this ds is also equal to zero. So that's how, like, there is two ways you can solve this problem. One is the straightforward, like the second law of thermodynamics, and next is like how I've done here, like to take the closed integral, and as d is not dependent on the uh, path that has been taken by the system, it's only depends upon the state of the system, as it's a state function. From there itself we can also prove that dq by dt in a closed integral will be equal to zero. Okay, so this will be option C will be the correct answer. Okay. Okay, so this is the problem 11. Now goes to problem number 12. So problem 12. So problem 12 problem. Ah, yes. So problem 12 is, which of the following is not a Maxwell's equation? We already talked about the Maxwell equations, right? So four options is given: del S, del V at constant t equal to del P, del T at constant V. Option B, del T, del P at constant S will be equal to nominal del P, del S at constant V. Option C is del V, del P at constant S will be equal to del T, del S at constant V. Option D was simply del T del P at constant S will be equal to del V del S at constant P. These are the four options that are given in the problem, and from this four option you have to figure out which is not correct, which is not aligned with the Maxwell's equation. Okay, so let me what I do. Let me now just copy this thing, Maxwell relation, to this that page. Okay, so simply to the copy, and here I'll paste it. So this is the Maxwell relation. Okay, so now if we see carefully, so first is del s del v equal to del p del t. uh, del s that is already here, right? So this is correct. Option C is, option B is del t del v at constant is del p del s at constant v. That is also there, right? This one, del p del s is constant v. So option A and option B both are correct. Option C is del v del p at constant s will be equal to del t del s at constant p. That is not here, right? Yeah, this is there, this, but this is this del. Let's check that option D, del T del P at constant and will be equal to del V del S at constant P. That is basically del this one. Okay, here should be P. Sorry, I think I've written. Okay. Mm. So this is not given, right? This option C, del V del P at constant S, del V del P at constant S. There is no del V del P, right? Del V del P del now del V del P. This is the option C is the Maxwell relation that is not mentioned here. So this option C will be the incorrect one. Okay. So this is the problem number 12. So basically, like the main reason of this type of problem that you should remember all these four formulas of Maxwell relation. That's why this problem is given. Now the problem 13. Okay, problem 13. Total entropy change for an isothermal reversible expansion is a 0, b greater than 0, c less than 0, and d any value can be possible. Ah. Isothermal irreversible process, total change in entropy. So isothermal means for this process dt was 0. Irreversible means it cannot be reversible, but I guess all of this information is not needed here because you already know, like from entropy law we already know if there is any irreversible process, for any irreversible process delta S will be always greater than 0, right? uh, Whether like this thing is I mean this all this information like isothermal reversal, these are like not needed actually, because from the statement itself you can easily tell that delta S will be always greater than 0 for this kind of problem. So this is the option B will be the correct answer. Okay, so now this is now we have already discussed like all of the 13 problems. Okay, so basically all of the problems like needs this concept of entropy, Maxwell relation, and all the like thermodynamic relations like relations between the Gibbs free energy, Helmholtz free energy, internal energy. All this relation basically needed was needed to solve all these problems. Okay, so this is it. So I hope you have understood all of these problems. So that's it. So now we'll conclude this session. Okay, so let's stop the recording first.